I want to start with a short story. So I'm not sure about you, but I actually don't like when things break, like really don't like. I've seen so many outages, but still don't like it. And one particular type of outages really stands out for me. So imagine you work in a small startup, small company, building like a classic online SaaS application. And well, your goal as a company is to increase the number of users by increasing sales, increasing conversions, doing all this stuff. And pretty much everyone in the company works toward the same goal, right? Engineers, product people, designers, marketing, sales, they all try to basically improve this channel. And you might spend like hundreds of thousands of dollars on advertising. And then one day, suddenly, your sign-up flow just stops working. So it's just like done. And all your customers, or potential customers, they just see never-ending progress bar. Well, you're an on-call engineer, right? You get an alert, you start investigating, and you realize that the new shiny microservice you just deployed for, I don't know, A/B testing or some new integration, or maybe generating funny project names, which is important, it just crashed, right? And your sign-up backend depends on that service, and so now the whole thing is down. It sounds unfortunate, and I was that on-call engineer more than a few times, and I learned that synchronous request-response communication in microservices systems can be really dangerous. And so today I want to show you how you can use event-driven architectures to avoid that problem. So just a few words about myself. I've been working for about a year at a company called Demonware, which is the part of Activision. And I also spent 5 years at Bench Accounting, which is now the largest online bookkeeping service in North America. And nowadays mostly do data engineering, but yeah, I did all this stuff before. So today we're going to hear two stories. First about Demonware, second about Bench. And before we start, just for the context, I want to introduce you to this problem. As you probably noticed, based on the number of people attending the microservices track, microservices are everywhere. And for me, personally, the problem of inter-service communication, I think it's really popular. And so I think a lot of people use synchronous request-response communication either with HTTP or RPC, and well, I think it's less than ideal, right? If you use it for everything in your system. And here's a typical use case. Let's say we have two services, service A, service B. Service A wants to call service B, so you might build a simple HTTP endpoint in service B, and you will send a request, right? So this sounds like an easy way to call a service. Well, if you really think about this, like how it works, you will notice that in order to even talk to service B, service A needs to know exact address, right? So it's the exact location of another service, which means it involves some sort of service discovery, which is not a simple problem to solve by itself. And by introducing this direct link between services, you also increase coupling, which we always want to avoid coupling when we can. Also, as we know, network is quite unpredictable. So when things fail, do you know how much time you should wait before you time out? Or how many times to retry when things fail? Or when to apply back pressure? Or how to use circuit breakers? Do you even have circuit breakers in your systems? Right? So my point is, you cannot make synchronous requests over the network behave like local ones. Just impossible. And well, a lot of companies, a lot of successful companies overcame some of the issues, and it's totally possible to build solutions for all of those problems. But I just think it's really hard to build solutions, especially if you don't have enough experience in these microservices environments and distributed systems, right? So those problems are really hard to solve. And well, if you use event-driven architectures, I think it's just more straightforward. Sometimes it's a more straightforward approach to solving some of the problems you might have, and it's a simpler one, and I'll try to prove it today. So just a few concepts to introduce before we go to the main section. If you use some sort of event-driven system or message queue, you usually deal with two types of data streams. It's either a point-to-point channel, where you have a one sender and a one receiver, or it's a publish-subscribe channel, where you have a single publisher and 0, 1, or many subscribers. And if you think about what kind of data you send over the network, we usually deal with events, right? So event is just a notification about something that happened in the past. You might also want to send commands over the network, and it's just a request to invoke some functionality. There's also a third concept called document, and I'm not going to really talk about it today. So our first story is about Demonware, and as I mentioned, Demonware is one of the Activision companies, and what we do, we actually build, mostly right now, we build Call of Duty games, and this is our latest launched game. And so at Demonware, we actually deal with some interesting scale, some numbers for you to understand. So we build and support core online game services. Some of them you can see here. We use Erlang for networking layer, and we use Python for application business logic. We still have pretty big monolith, number of reasons, but we're slowly migrating to independent services, SOA. And historically, we used a lot of synchronous request-response communication, well, just because it's easy. And we used HTTP and RPC and all kinds of different protocols. But conceptually, we have the same approach with this communication style. The producer usually knows exactly which service it wants to call into, right? And it's also aware of the action that is requesting. And usually, it needs to be notified about the reply, right? So it wants to know what happened. And so this is a good model. This is how people build systems. This is how we've been building systems for a while. But well, we found that we will have some value in implementing asynchronous communication between services as well. Right? It's currently work in progress, but I think we are in a pretty good state right now. And we decided to use domain events to communicate between services. And well, in this model, the producer, the event, it can be handled by 0, 1, or many consumers or processors, and each of them can have its own goal, its own way to handle data. But again, you don't need to really know about it as a producer. So it's a very, very typical pops-up approach. And in the end, you're also not really interested right away about the result of that operation. So it sounds very straightforward. And well, one benefit you get when you implement a system like this, you can integrate all those events, all the streams of events, with your data pipeline or data warehouse really easily. And so we really like this approach. And so this is how our typical service looks at Demonware when it consumes and produces events. So we heavily use domain-driven design. We love it. And what you see here is called hexagonal architecture, or onion architecture, or clean architecture. It has so many names. But conceptually, you have this application core which contains all the business logic for your application. Right? So it's all pure business logic. It doesn't include any sort of integrations or third-party systems, nothing, just your application. And it might include persistence logic, it might not, it depends on the use case. And so in this model, when you want to expose this application core using some interface, you add adapters, right? So you want to build HTTP API, you add HTTP adapter, and so this adapter actually handles all kinds of serialization, deserialization concerns. It handles configuration, all the endpoints. So basically, it contains all the HTTP-related logic, and it only calls your pure business logic in the application core. So again, it sounds straightforward, but you don't always build systems this way. So if you want another interface, let's say you decided to expose your tool via command line interface, you just add another adapter. And in our case, if you want also consume events, it's just one more adapter that's called event adapter in this case. And so we have this message transport layer implemented in Apache Kafka. And you send events in Kafka, and this event adapter consumes the event, and it deals with all kinds of, again, serialization, deserialization logic, transformation. It knows how to route this event and what exactly to call in the application core. So it basically transforms all the events to a series of commands, and then we just execute those commands with the method calls. Right? So it's very straightforward here. And then we produce, well, in the application core, when some logic is triggered, it can produce another event as a result. So in the end, we have a closed loop, right? So consuming, producing events using the same transport. So I mentioned Apache Kafka. If you're not really familiar, it's the concept behind Kafka is very straightforward. You just have a single event log that's partitioned and replicated, and it's immutable. That's it. So in Kafka, when you have a topic, right, usually you deal with named topics, and you can create a topic, and in this case, you'll have multiple partitions. And so as a producer, you would write your messages to one of the partitions, usually chosen randomly. But as a consumer, you have to consume from all of those partitions from a series of topics. And if you remember those types of channels I mentioned at the beginning, if you need a publish, subscribe, or point-to-point channel, it's usually a decision that's made in the consumer side in Kafka. So consumers actually dictate what kind of semantic you want to get. So in this case, let's imagine that on the left side we have this group A, and let's say we assign a different consumer group ID to each instance in group A. So in this case, when a new message arrives in Kafka, each of those instances will receive a copy of the message, right? So it looks more like a publish-subscribe interface in this case. But on the right side, we have another group, and let's say in that case, every single instance will have the same ID. So when a new message arrives in Kafka, it's going to be delivered to only one of the instances, right? So you kind of have a point-to-point semantics here. And so we use service name as a topic name in Kafka. And when services start, they need to basically explicitly subscribe to all the interested topics. And then we also partition all the data using the user ID. So we can actually preserve the ordering of operations for a single user. And this is what a typical high-level consumer architecture looks like in this case. So on the left side, you have a Kafka topic with a number of partitions. And again, all the user events are usually within the same partition, so we keep the ordering. We use Kafka Python Consumer, which internally uses Liberty Kafka C library. And this consumer pulls the data from Kafka and keeps it in the local buffer. And then we use a series of Tornado queues. So Tornado is a non-blocking IO framework for Python. And so each queue usually represents a user, so it really mirrors the partitioning structure. And in that case, you can have a non-blocking IO all the way to the event dispatcher, right? So you don't block when you wait as a consumer on Kafka. And event dispatcher handles all kinds of serialization, deserialization logic. It knows it's configured to handle a particular type of data, and then it calls the application core business logic in the end. And here's a very simple example of a consumer. You can see a simple Python class called service A events dispatcher. It uses this decorator called dmonada event source. Dmonada is the name of our internal framework. And event source just basically says, hey, this dispatcher is interested in this type of events. And somewhere in our configuration, we actually map these events from service A to a set of Kafka topics. So it's not really done here. We have a separate configuration for that. And so now this dispatcher consumes data from a set of topics, and it can have many callbacks, right? So we have a single callback here called onUserUpdated, and with another decorator here to say we are interested in this event schemas. So we have another decorator called Demonware event schema, and we say we want user updated events. We can actually specify what version this callback supports. So we can actually specify version explicitly, or say it should be greater than or equally 1.1.2.3 or something. And we also specify what kind of DTO, data transfer object, which usually a simple Python dictionary, should be used. And so when this onUserUpdated callback triggers, it actually receives the event as a Python dictionary, and then you can basically deal with this event and understand what kind of business logic you want to trigger in the application. If you look at the producing side, our producers support multiple reliability guarantees. And if you deal with Kafka producers, by default you know that any Kafka producer library supports this acknowledgement option, right? So when you write to Kafka, you can say, I don't even want to wait until the first broker replies to me, right? So it's, in this case, it's 0. Or you can say, I want to wait until at least one broker replies. Or you can say all of them, so all within the same replication group, so not the whole cluster. And this sounds like it's a good enough reliability guarantee, right? If you use all, so you have at least maybe like 3 Kafka brokers. But what if you have some really sensitive data, usually around finances and all that, that you wanna deliver 100%, right? So if there is an application entity update, so you updated some user or some entity in a model, and you also triggered an event, and you want to deliver that event for sure, like just guarantee. And if you just use that single approach and your Kafka cluster is down, then interesting things can start happening because, well, you probably start retrying. And then again, what if the Kafka cluster is down for an hour, for 4 hours, maybe the whole day? You just cannot fix it for some reason. I don't know. Like, can you promise that your application service can retry for 4 hours and nothing happens? Not a memory exception, or maybe you actually need to restart your application in order to fix some Kafka issues. So you basically you will lose this retrying state because it's just a memory. So it's not good enough, and we decided to introduce a very simple, very straightforward workaround where we write all the events to an event store backed by a database. And in this case, your application only cares about the event store, and then there's a special process that actually reads the data from event store and tries to sort of reconcile it eventually, right? So for you as a producer, the most important thing is just to write to the event store, and that's it. And so we came up with this. Well, actually, there's also a third option, sort of intermediate one. If you don't want to really provision in your database, but you still want to have more reliability guarantees, you can also use event store backed by a local disk and use something like RocksDB or BerkeleyDB and just keep data locally. But in this case, if your application instance crashes with a hard drive failure, then you lose the data as well. So it's a compromise. And this is a very high-level representation of that producer. So again, you have application core. It triggers some events or maybe commands in different architectures. You have an event publisher that knows how to deal with those events and how to serialize them. And you write them to the event store. And then there's a special process that actually reads them and we use Kafka Python Producer, the same framework, and then you just write to a Kafka topic using the same partitioning guarantee. So you always partition by a user ID. And here's an interesting detail here. If you use the same database for your application entities and the same database for your event store, a relational database, you can actually support transactions and have transactional guarantees, which might sound, well, the first part of the sentence might sound like it might be not a good idea, right? Because you're supposed to use, different persistent engines for different use cases. But here, well, it's really great. It's a huge benefit if you can actually support real transactions for that. And so in this snippet, first few lines, we just do some reads, and then we, lines 6, 7, 8, 9, we do some sort of business logic, doing some reads as well. And in the end, we have a new entity, and then a new event. And so our goal is to update the entity in the database and deliver an event with 100% guarantee. So what we do, we actually create just a simple transaction. We update an event in the database, and this publisher.publish call, it simply triggers my MySQL insert statement, right? So we have update, insert, commit, and if one of those fails, then we roll back the whole transaction. So it's very straightforward. But in the end, what we achieve, we can say 100% that if we updated an application entity and triggered an event, we're going to record this event in the event store, and then eventually, when Kafka is recovered, we can actually reconcile it and maybe apply some necessary changes later. It's fine. So as a summary, at Demonware, we use decorator-driven consumers with callbacks. We have different reliability guarantees for producers. We have non-blocking I/O using Tornado. And we also use Apache Kafka as a transport. But still, can we do better than that? So if you look at this snippet again, and you try to understand conceptually what it does, you take a bunch of events, right? You have a lot of configurations here built in, all those IDs, decorators. And you also have a bunch of callbacks here. And this example looks somewhat straightforward, but imagine that you need to consume 100 of different event types, and you have, like dozens of services. And if you end up writing all this translation logic over and over and over and over again, it might look really complicated in the end. Because the only thing that callback does really, it takes one type of data and it tries to translate it to another type of data and then just call the application, right? So it's a lot of writing, but that's just the way it works right now. And I was thinking before joining Demonware, before implementing this system, can we create producers and consumers that support message passing natively? There's an answer for that, actors. So if you're not familiar with actors, actors actually, it's a really simple concept. Actor is an entity that communicates with asynchronous messages instead of method invocations, and they can manage their own state. And when they receive a message, they can either create other actors or send messages to other actors or stop actors. So that's a very simple model. And every time when I talk about actor models, I love this example. So if you want to understand how actor models really work, and if you want to understand all the constraints, imagine this situation where you just have a few friends and they decided to only communicate, using old school physical mail. So no phones, no text messages, no messaging, no apps. You just send an old school letter, and that's the only way you communicate with your friend. So if you think about a system like that, you can actually quickly understand all the constraints that your system has, because even if you write a letter and you have an address and you send that letter, you have no idea how much time it exactly takes for that letter to be delivered. And actually, you also have no idea if it's going to be delivered at all, right? And if you expect a reply back, you also have no idea if it's going to be delivered or when. So you just hope. And it sounds like it's a very unreliable system, but what is the closest representative? What's similar system that you can think of? Well, it's actually network, right? So that models network really well. And well, actors were introduced. I don't even remember what language, but they were made popular in Erlang a while ago. And in Erlang, actor, well, here it's just a function, really, that has a receive block. And this receive block, it contains all kinds of rules for all the incoming messages, to be processed. So when it receives a message, it can check all the cases in a receive block and understand how this message is supposed to be handled. And in our case, we just accept all the messages and we simply print it and we send the message back to the sender. So this exclamation mark operator here, that's just a asynchronous send command. You can also implement actors on JVM using Akka framework, and conceptually it looks the same. So we have a class that implements this actor interface. It also has the receive block, just implemented as a function, as a partial function with a bunch of case statements. And so the same example, we accept every single message, we print it, we send the message back to the sender. Got it. So if you think about actor-to-actor communication, it's always asynchronous, it's always non-blocking, and it's always message-based via message passing. By the way, it doesn't mean that you just have to send a message and then wait, indefinitely, because timeouts can and should be used. Location transparency is a really big deal. So if you're not familiar with the concept, what it really means, if you have two actors, actor A and actor B, and actor A wants to send a message to actor B, it doesn't really matter where the actor B is located. It can be located in the same JVM process, it can be located in the same machine, or it can be located in a different machine, in different data center maybe. It doesn't matter because the interface to communicate with that actor is the same. And I think it's a really big deal. And when you start working with this, actor-driven systems, you realize that you don't use, maybe like Java OOP patterns or some sort of patterns that you use when you deal with classes and methods and functions and all this stuff. You realize that the whole system starts to look more like a messaging system, like a event-driven system, like a messaging queue maybe. And so if you look for patterns in this case, I highly recommend the Enterprise Integration Patterns book from, I believe, 2003, so 15 years old, but it's still so relevant. And it contains, I think, 60 plus different patterns that you can use, and it was originally implemented sort of as a way to design message queues and messaging solutions and enterprise service buses. But again, it's still really relevant right now if you implement all kinds of event-driven systems. And if you want to use all those ideas in actor models, one of my favorite authors, Bon Vernon, he actually published this book a few years ago called Reactive Messaging Patterns with the actor model. And what he did, he tried to take all the ideas from enterprise integration patterns and apply them to actor models. And I think it's just a really, really great resource if you're interested in this stuff. So I highly recommend you. So now our second story. If you're not familiar with bench accounting, again, it's a classic online SaaS application for doing your books if you're a small or medium business in North America. And this application is used by all the customers and also all the internal bookkeepers. So what we did, we actually built the whole bookkeeping tool chain from scratch. So we didn't use any external software. We implemented all kinds of reporting, reconciliation, receipt collection, and even some OCR, And we built a lot of integrations with different banks and statement providers and all this. And originally, it was a big enterprise Java monolith, but we transitioned it to a series of Scala microservices with akka, so using an actor-based approach. And we implemented a legacy event-based system a while ago for application notifications. But that system wasn't really good enough going forward, because it was designed for just a few specific use cases, so the event schema wasn't extendable. And it just wasn't built for microservices because, well, we had monolith, and it had a bunch of coupling with different internal systems. And we also got a bunch of new requirements. We wanted to introduce real-time messaging for our web and mobile clients, and we wanted to have a framework for producing and consuming different domain events and commands, so both point-to-point and publish-subscribe channels. And otherwise, it looked really similar to what I described for Demonware, so pretty much the same asynchronous communication model. And again, this is what a very high-level diagram of a inter-service communication looks like. And you can notice something interesting here in the middle. So when service A wants to call a service B in this model, how it happens, we used ActiveMQ here. And well, it was a few years ago, so ActiveMQ was a decent choice. And nowadays, you might as well just use Kafka or some other message queue. It's not that important. But I'm just going to use ActiveMQ here as a reference. And so when you send a message, when you want to send a message to, from one service to another, first you send this message to, a single ActiveMQ queue. So it goes into that queue. We have this special eventing service in the middle that consumes it, writes the event into the event store, potentially also, triggering some integrations, and then it tries to deliver a message over a queue or a topic, and in the end, service B receives it. And so I mentioned ActiveMQ, and if you try to implement point-to-point or publish-subscribe channel in ActiveMQ, it's actually really straightforward because for point-to-point channel, ActiveMQ has the concept of a queue, and it's a simple first-in, first-out queue. So a single message in, single message out. And for publish-subscribe channel, we have topics. And topic, it's a single message in, and then many subscribers. But here's an interesting point. If you deal with ActiveMQ, you know that. But if you knew, when you use topics and you have multiple consumers, and one of the consumers is down, then all the messages they are not going to be delivered to that service. Well, because it's down. But when it starts, it's not going to receive any messages. It's skipped. So they just completely lost for that consumer. And there is a feature called virtual topics that you can use to basically represent a single topic with multiple subscribers as a series of queues internally. For you, it's completely transparent. You don't need to think about that too much. It's just a bunch of naming conventions. But in the end, you can actually get publish-subscribe guarantee on ActiveMQ with a guaranteed delivery. So this is exactly what we wanted. And we also use service names for naming our queues and topics in ActiveMQ. But there's also a special topic for what we call global events, because some services are actually interested, in the same event all the time, and we just dedicated a special topic for that. And services can subscribe to interested topics basically anytime a new actor is created. So it's great because you can do that in runtime. You don't need to restart your application, or you don't need to deploy a new version. You don't need to change configuration. If there is a way for your application logic to understand, now I need to listen, for this particular topic or for this particular queue, it can actually just create a new actor and done. It works. And in this model, we support 3 different modes of operation. So we have a point-to-point channel. And in this case, it's actually a perfect fit for commands, right? So if you want to command a service to do something, use a point-to-point channel and use an ActiveMQ queue mechanism. You can also use a publish-subscribe channel, and you would use a virtual topic in this case just to achieve this guaranteed delivery. And well, for that global events topic, we also have a global publish-subscribe channel. So it's also available for a service to use, and it's also a guaranteed delivery using this virtual topic feature. Our secret sauce, Betcha Camel. I'm sure if you heard a lot about this, but it's actually an integration framework that implements those enterprise integration patterns that I mentioned a few slides ago. And there's an Kafka Camel official Kafka library. It's now deprecated, and there's an alternative, but I think Kafka Camel is still great. It still just works. But you know, feel free to check both libraries. And it can be used with Java or Scala. And my ex-colleague GM once said, it's the most unknown, coolest library out there. So trust GM. This is what a typical consumer site would look like. So we have an ActiveMQ QR topic on the left. We use internally this ActiveMQ Consumer. So it pulls data and it keeps data in this prefetch buffer. And then we just trust Kafka Camel to do all kinds of translation and deserialization. And basically it knows how to talk to ActiveMQ Consumer and how to talk to the actor model. So it takes all those messages and it translates it to a series of messages to your actor. And it's great. Very simple example. Let's say we have this customer service implemented as an actor. We have an endpoint URI. It just a pass to some sort of ActiveMQ topic, and usually you would configure it in your configuration file somewhere or environment variable. Here is just plain text for the sake of example. And then we have this receive block, and if you check at the bottom, so line 9, 10, you see this delete command, delete account command. And so this is just a typical message an actor can receive, and usually what happens, another actor in the same system, would send this command if it decides that particular account should be deleted. So we can just send a message to this customer service and say, hey, please delete this account. And well, you trust the other actor just because you run the same VM, the same actor model. But another actor remotely can also trigger this command. And what we implemented, you can also, call the same functionality over the network using the queue. And in this case, we have a special camel message wrapper. So Kafka Camel by default wraps all the messages in this Kafka Camel wrapper class. But you can use some implicits, Scala implicits, and some magic to basically quickly understand what kind of type this event is, and then just translate it to the delete account command. So you trigger the same logic. Just the way any other local actor would do it, and you do it literally with just a single line of code. And it's still some translation, so I still don't like it, and I still think that if you spend enough time playing with the Scala implicits, you can just completely eliminate the first case. But we just decided to keep it because it's very expressive, and you sort of know what happens, and you can add some additional logging here. So we decided to stick with this. And our producing side, again, very similar to the consuming one. It's very straightforward as well. So any actor can just decide to send a message to another destination at the service, and we use Kafka Camel for serialization and all kinds of routing and configuration. And we use ActiveMQ Producer in the end to produce data to a topic or a queue. This is what a typical usage of an event publisher looks like. So we have a few examples here where we, in the first case, we just want to do sort of a classic pub sub. So we construct some sort of event, and then we can broadcast this event. In the second example, we want to send a command. So it's still called event.bankerror, but that's just an example. So we can generate this command and then send it directly to a specific service. So that's another use case. And remember I mentioned this eventing service, so like a special thing in the middle. So what it does, it actually listens for all the events and commands you publish. It receives all of them, writes it to an event store, and then acknowledges every single message. So a producer knows that the message was at least delivered to the event store. And then it tries to forward the message and deliver it to the destination. So why do we need this router service in the middle? Well, actually, if you have something like that, then all routing logic is handled in one place. And if you decide to iterate on it, you don't need to redeploy every single microservice in your system. You just redeploy a single piece of software. And all your producers, they just know how to talk to the eventing service. They don't need to know how to talk to all the other services in the system. So it's a simple router in between. And because of that, we can actually simplify all the consumers and producers drastically, right? Because they just need to do one thing well. And in this case, you also have an event store that contains different types of data, right? So it's super useful for all kinds of data analysis and some other use cases. So it's just great benefit if you can sort of combine different data from different services and put it in the same place. So as a summary, event framework in bench accounting, it's actor-based, using consumers and producers via Betcha Camel. Producers can acknowledge messages, and it has a non-blocking I/O just by definition because we use actors, and we use the Apache ActiveMQ as a transport. So now some of the lessons we learned, building all this stuff. If you think about actors, I think that semantics, it's really important. It is a huge benefit that actors support message passing natively. And if you think about asynchronous communication and location transparency at the same time, by default, it is really easy to migrate actors between the services and migrate them between the boundaries over the network. Again, because it's the same way for an actor to talk to a local actor, and it's the same way for an actor to talk to a remote actor. So if you have a monolith and you implemented part of it as an actor system, then you can migrate, most of the actors over the network, and you don't really need to, build APIs and clients and schemas and all this stuff because, well, the asynchronous communication just handled for you. And I can also talk about some other benefits, but it's probably a topic for the next presentation. So some of the recommendations, I still love domain-driven design and enterprise integration patterns. Those are really relevant nowadays, especially because we build and we deploy more and more event-driven systems. And you should really understand your domain space, and you should really understand if you want to support events, commands, or documents, or all of them. You will have to handle, you will have to explicitly handle every single failure in this case because, well, they will happen eventually. And an event store, it can be used for so many things if you implement it properly. Just for start, you can use it for tracing and all kinds of debugging, but later you can also use it for auditing. And if you don't have any sort of data platform, data lake, or data warehouse, it can be just the first attempt to have a thing like that. So actors or not, it really depends. I think I just showed you that it's possible to build asynchronous non-blocking systems with languages like Python or, well, maybe Node.js or Java. But of course, if you use a language with actors, I think it's a really great fit for all this asynchronous communication in the end. And I think that now you should really, if you want to implement a system like that, you should really consider what messaging or what transport layer you should use, because, well, Apache Kafka is great and it can handle really impressive scale, but at the same time, it wasn't really built as a general purpose messaging queue, right? And it lacks some of the features, and some of them were just recently introduced. So you should carefully understand what you want to use in the end. And you need to also understand if your use cases are, depending on low latency or high throughput, and in the end, it's perfectly fine to have different channels with different characteristics. And do you really need exactly one semantics? It's really expensive to have it, and I don't think that every single use case in your system needs it. I didn't have a chance to talk a lot about message formats and schemas, but those are extremely important, and I'm happy to talk to anyone about this stuff because I love it. And I think personally that you need to choose binary formats like protobuf or avro. But if you use something like JSON, then please invest into schema registry and design a schema evolution strategy before you start sending a bunch of events in production. And also another really useful technique. If you deal with a bunch of messages in your system, I would consider splitting them into the envelope or metadata and the payload. And events and commands could probably share the same envelope, and different types of events could also share the same envelope. Finally, some challenges. The main challenge, obviously, we're still too attached to the synchronous request-response paradigm. It's just everywhere. And it takes time to learn how to live in this asynchronous world. I believe that high coupling will definitely kill you. What I mean, when you have just a handful of services and a handful of event types, it's kind of obvious how to route all those events and how to deal with all those publishers, producers, and consumers. But when you start to have 10 plus or 100 plus or even more microservices, and you just maybe stick to the synchronous paradigm, or you use commands, which is also a very synchronous style in its nature, the coupling will just kill you, right? Because it's very hard to maintain all the connections between all those things. And I recommend to stick to events as much as you can and use commands, in very rare use cases. And it's still a big challenge to, if you run Kafka, for example, it's still a really big challenge to maintain, a properly partitioned, replicated, monitored message broker cluster. So, if you can rely on things like Kinesis or, Google's PubSub, managed services are gonna make your life easy. Finally, I think that it's actually, if you just want to start implementing a system like that, it's really straightforward to replace your writes with events. But it's really hard to replace your reads. And, well, sometimes it's fine to just use synchronous communications for some specific use cases. But if you want to fully embrace microservices and event-driven systems, you will probably end up with something like database denormalization, or some sort of in-memory data structures, or caching, or stream processing. So previous presentation was actually a really good example, how you can deal with different sort of read and write paths. And when you have really a lot of producers and consumers just scattered across the same service, it starts to feel really complicated to see the full picture. So I learned that if you use state and sequence diagrams, you can actually see all the business use cases easily. And you will probably end up with some sort of distributed tracing in the end, because when you have a lot of those producers and consumers, it's just a requirement. And obviously, it's also a requirement to have a proper monitoring and alerting, just because when you deal with synchronous communication and things fail, you usually understand it right away. You see some sort of 500 error page. But here, you send an event, and then you expect a reply back. When things fail, it might be really hard to understand that it's actually happening. So you need to invest in a proper monitoring and alerting. And remember that sign-up page use case I described at the beginning? So, well, the solution was really simple. We just kept the critical path for the user sign up, really slim, and in the end, it would just trigger an event that a user has signed up, and we built all the other integrations and all the other systems around this event as consumers. I just want to really thank Davide and Pavel because without their help, this presentation wouldn't happen. Now I'm happy to answer any questions, and I believe I have time for a few questions now.
Any questions?
Right there, in the middle. No. Oh, at the back.
Hello. Eventually, you have small services that talk to each other via events, but where is the orchestration happen? Because you need like a full business logic to talk to this service, and it produces even to that service. So,
well, the moment you introduce some sort of orchestration, that's your bottleneck, right? So that's why I mentioned something like sequence diagrams. You just have to keep track of this, and you can hear something like a service mesh or some other tools that people use nowadays, but they don't really help you with this right path that I mentioned, right? So if you use events to just trigger some actions, that's just the way to go, right? And you rely on monitoring and tracing, but in my experience, you just don't use any sort of orchestration on top of the system because it's perfectly good, by itself. I hope I answered your question. Any other questions?
One more over here.
Yes. I'm just asking right now about in case of multi-clustering. How do you handle if you have multiple consumers and all of them are going to do exactly the same? You have multiple clusters, each one doing the same action. So how are you going to handle this if you are going to have multiple actors doing the same to affect something in database? So multi-clustering mechanism that you are following.
Oh, I see. So when you use actors are usually stateful, right? So what you can do, if you have some sort of service that does some database writes or some, deals with some sort of integration, you can actually keep state inside an actor, a single actor. So you don't really have this concurrency issues, if I understand it correctly, that's what you're asking, because every actor just deals with a single operation by itself, right? So when there's a write request, it just goes to a single actor, which is atomic inside. So in the end, you just don't have this, concurrency problems that you might have when you deal with, classic databases. Right here.
Last question.
Should our services be slim as possible, or is there any overhead or balancing issues on there too? Because at some point, we begin to use the messaging queue more and more, and will it bring some weight to throughout the system?
Yeah, that's a question about microservices boundaries, right? And basically all the trade-offs, and that's a whole presentation by itself. But what I like to refer when people ask a question like that, check bounded contexts in domain-driven design. So you can actually understand what is the proper border for your specific domain use case, right? And it can go as as wide as a monolith to a really small microservice with 50 lines of code. And yeah, I don't think there is a very generic recommendation that you can just use. And I would prefer to always go from very big services to smaller services, and in the end maybe microservices when you need to, right? But I wouldn't go to like hundreds of services from scratch just because it's cool or more reliable or whatever, right?
Great job, Yaroslav.
Thank you.